The discussions we have had so far for this module is all about continuous time. That means everything happens continuously. There's no break in between. And if you look at them as kind of mathematically, the functions are defined as a function of time, which is continuous. Time is continuous. The Laplace transform deal with continuous signals. The transfer function is the same. It's derived from Laplace transforms. Okay, they all deal with continuous time, and continuous time, you will have continuous time controllers. Now, if you try to implement continuous time controllers in practice, you would have to use analog devices. That's why sometimes we also refer continuous time systems as analog systems. Now, in contrast to that, we also have something called discrete time or digital control systems. Now, discrete or digital means one thing, discontinuous. Okay? Now, discrete time system breaks time into different intervals. So they're not continuous anymore. So you start from, for example, from 0 second to 1 second. So nothing happens between 0 and 1 second. And then the next interval will be 2 seconds. If I choose a different interval, I could have interval 0.1. Then the first instant would be 0. The second instant would be at time 0.1. The third instant would be at the point of 0.2, and so on, and so forth. It doesn't really care about what is happening in between the intervals. And it can't, because the way the discrete time is implemented. Now, digital control is slightly different in that it's a particular special case of a discrete time. And not only you will have intervals in time domain, but the values you are dealing with are also discontinuous, because we use digital numbers. Digital numbers are not continuous. Okay, so you have 0 and a 1 and 0 and a 1, or and things like that. You don't have strictly. You don't have floating point. You don't have decimal points. And therefore, because they are not continuous, we call them digital. Nowadays, because computers will have a high precision, they have many different memory space, and therefore you can actually use a lot of zeros and ones to represent a number. That makes the difference between discrete time and digital control very negligible. So people often just mix the two together, not to worry too much about the difference between the two. But there is a difference. Okay, discrete time is focused on discontinuous domain for the time. Okay, so the in time is discrete or discontinuous. Digital control means it is discontinuous in both time and values. Okay, so but because we have better computers nowadays, so we tend to worry less about these things like that. So in the next few sessions, I'm going to first by introducing the basic structure of a computer control system or digital control. Okay, and then we're going to talk about how to process the sampling and Z transforms, which is really the mathematical way of dealing with discrete or digital control systems. It's very similar to the Laplace transform, but in discrete time or in digital domain. And then we're going to look at some control design methods. If I show this diagram here, this is really the difference between continuous and discrete and digital. Now, for the continuous time, the controller deals with continuous signals. So your input, that's for example here, for your reference, is continuous. Your feedback measurement is also continuous. And the difference between your input and the feedback measurement is dealt with continuously. It doesn't really wait for the next time instant. Whereas in the discrete time control, the reference happens only every time interval. The feedback is also processed every interval. So there's some gaps in between that the controller doesn't do anything at all. Okay? And the reason for that is the discrete time control is typically implemented by computers. Now, computers take time to process. Okay, so if you have a set of value comes in, one value comes in here, and this value comes from the feedback, the controller has to take time to calculate what actions they need. Unlike analog devices, they work continuously. Okay, computers take time. Even for the very fastest computers, there's still a finite time for each calculation. Okay. That's why they have to wait for the intervals. And as I said just earlier, continuous time means continuous in time and value. Discrete time means discontinuous in time. Digital means discontinuous in both time and values. But the difference between discrete and digital is really negligible nowadays, because we have better computers. Now, if you look at the basic continuous control system, this is what we typically have. We have a plant. This is object, plant or process. This is the object for control. We have measurements. We need to take output, measure the output, send this back as feedback, compare with an input. The difference here is processed here. So really, there are only very simple blocks. Okay, so you can actually say this is a plant, this is a sensor. Now, notice that the plant in the real world tend to be continuous. The sensor, most of the sensors we use will also be continuous. So it suits the continuous time controller very well. Okay, and so you would have, for example, before the computer age, you would have some kind of electronics board to implement the controller you design. Okay, and it doesn't involve, or it did not involve, any computers at all. Well, people didn't have computers at that time. Now, for a digital system, however, things get slightly more complex. What we have is you still have the plant. This is what you want to control. You still have to take sensors, but then because the controller tend to be implemented in computers, computer takes time. Okay, therefore you have to have some interfaces with the real world. Okay, so the green block now represents something inside of a computer, or the entire control system. Okay, but the computer has to talk to the real world. If you think about the computers nowadays, you have zeros and ones. In essence, all the calculations inside a computer are dealing with zeros and ones. But plant doesn't know that. Okay, plant, for example, if you drive a car doesn't know any zeros and ones. It has speed. The speed is continuous. You probably have power output from an engine, that's continuous. If you use a sensor to measure the power, or measure the current, or measure the force, they tend to be continuous. And they're not zero and ones. So you need some kind of interface to convert the measurements you have into and zero ones. This process is called analog to digital conversion. So with the device, so as part of your control system, together with the computers, you will have something called analog to digital converter. After the computer does all the work and calculate everything, it says, okay, this is what I want the plant to do. But the values will be in the form of zeros and ones. And computer doesn't know any zeros and ones. Okay, so you have to somehow convert the zeros and ones into, for example, voltages, and then you can feed that into the control into your plant to say, okay, this is now I have the numbers or the values that you understand. Okay, so there's two devices here, A to D and D to A, and they are essential. Okay, A to D stands for analog to digital conversion. It's essential for converting measurements into zeros and ones. D to DA converter stands for digital to analog converter. It converts zeros and ones into voltages or other continuous quantities that the plant will understand. Okay, but there's also a clock. Now, when I say a clock, it's really not a clock in the conventional sense. It's what it is a timer. It ticks every so often. Say I want an interval between, say, interval of 0.1 second, so that clock will tick, will give the controller a nudge, if you like. Say, no, this is my next 0.1, and then at 0.2, and it will give the controller another nudge, say, do something, wake up, do something. And so that's interval rather than a clock. It gives typically it gives a controller a regular pulse to say, no, this is time up, you need to repeat your calculations. Okay. Now, because of this need for the computer to take time to do the calculations, that's why. So you have to define what that interval is, and then when you design a digital controller, you have to make sure your clock or the timer gives a nudge every interval time. Okay. Now, also because of this interval time, we have other issues related to the analog and to digital conversion, or digital to analog conversion. So if you think about analog, because computers to analog to digital conversion first. Now, the real reason for using analog to digital conversion is to convert analog measurement into zeros and ones. That's really that part. But because the computer does things in intervals, it takes time. It can't do this conversion all the time. So what happens is that it does one conversion and wait for the next signal from the clock. So now take another signal and then convert that zero and ones. Okay, and then wait for the clock to give another signal after the same interval. Okay, so the conversion from analog to zeros and ones happens not continuous, is actually in steps. Okay, or officially we call that sampling interval. Okay, because it takes data in, convert that into zeros and ones, and then wait for the next interval, and then take another data in, convert that into zeros and ones. So this is known as the sampling interval. D2A, on the other hand, D2A converter, on the other hand, it converts what computer calculated into analog signals. But then you have a problem there, because the computer takes time to calculate, and it can only give you an outcome at every interval. But plant doesn't want to wait. So what happens to the plant? It can't wait for a next signal coming and do nothing in the meantime. So what would happen in this case? We use something called zero order holder. I'll explain that in a minute, okay? But the message I'm trying to give here is that for either A to D or D to A, there's an extra element there, okay? A to D, there's a sampling process, and that takes place every t second, every interval, i.e. D to A, there's also extra part to it, that's called zero order holder, okay? It holds a value for in between the intervals, okay? But I'll use an example or I can explain that graphically. So this is the sampling process. As I just explained, the computer can only take in data and convert that into zeros and ones once every interval. Say my interval is t, okay? The input signal here is a continuous time signal. That's my xt. And interval is t, so the computer would take one value in, convert that into zeros and ones, and then wait. It doesn't do anything else because the need to do the calculations. So the computer has to wait. Or what? It doesn't wait. It's busy doing other things. It can't deal with another signal yet. So essentially, you have to wait for the next interval. So at the time t, it will take another value in, convert that into zeros and ones, and then the computer will go away, do other things, and come back until the clock says, oh, it's a time again. So you need to take another data, okay, another data, and convert that into zeros and ones. So it goes on like that. Now it works well when you have a good sample interval. Okay, if you select a time interval sensibly according to requirements, then you will get a set of values fairly, with no dramatic changes. But if you don't get your selection or your sampling interval right, then you could have a problem like that. Say I use t, but I'm using that interval to convert a different signal into digital values. Now you can see here, there's no problem in between here, there's no problem there. You are catching on pretty much everything. But between these two, because the continuous times dips in between the interval, you would miss the entire dip altogether. And the computer will treat this signal in the same way as that, because you can't detect it. There's nothing you can do about that. In this case, you would need a faster computer, or you need a much smaller interval in order to process that, to not miss that dip. Okay, there are two ways to deal with that. One is to say, right, the computer have some kind of capacity to detect certain faster changes, and then reduce the interval accordingly. This kind of approach is commonly used in computer simulations when it doesn't have to deal with signals in real time. Okay, but for our controllers, which tend to be implemented in real time because you need to control something that's for real, and you take a more blanket approach, you reduce the interval altogether for every time. Okay, so I added a lot of intervals here, and you'll end up with, of course, a lot of data to process, or the computer will have to process. Therefore, you need a faster computer. So that's the potential issue for the A to D or for the sampling interval. Now, sampling interval, sometimes we call it sampling rate. We also sometimes use sampling frequency, which is the inverse of the sampling interval. Okay. in hertz. If it's in hertz, that's 1 over time. So we need to be a little bit careful there with how to select the interval, and we will discuss a bit more about that. What is the rule? What is the guideline to select that interval for control systems? It's one of the very important decisions for the design of controllers or control systems. Okay. Now, on the other hand, the D2A conversion. Now, the computer does things. Okay, every interval. So it says, right, this is what I want to do for this interval. So it needs to send the signal out to the plant. And then it doesn't really do anything because it does something else because it's busy doing other things. It won't be able to give you an output until the next interval, t. So you have this red dot there. Okay, forget about the blue lines for the time being. Okay, so you get another dot there. After another interval, the computer will give you another value, and so on. So you have all these red dots coming out of the computer. The plant doesn't like that. In an engine, if you drive a car, the engine can't do them in a sort of impulses. You can't say, right, you're going to give me this much fuel, and then you stop giving me fuel, and then after a while you give me another fuel, and then stop giving me fuel. It won't work. It will not work nicely at all. Okay, it wants a continuous feeding of energy or fuels. So to solve a problem like that, and attached to a D2A conversion will be something called a zero-order holder. What that does is, if the computer keeps a value here, this zero-order holder will hold the value, will keep the output at that value for the entire duration until the next interval comes up. Now, by the time you get to t, the computer will be able to give an update. So you get this value, the output goes up, and then the ZOH will keep that value until the next interval, when the computer is ready to give another signal. Okay? And so on. So it goes on like that. So therefore, it's not really sort of very smooth kind of output, but it's kind of doing that in steps. Okay, now that obviously is not ideal. But because the computer can now do things much faster, we can actually reduce the interval as much as we could. Therefore, this sort of bumpy rides, all the steps can get smaller and smaller. You can actually reduce the step sizes. But there is always this limitations. The limitation for the A to D is the interval, and you lose the signals. If there's a risk of you lose signal, even if we're not losing the signals, like in between here, and the input is continuous, but the computer doesn't really know what is happening between here. It only takes that value in and take that value in. Okay, so there's disadvantage there. And although the disadvantage is sort of minimized nowadays because we can actually have very fast computers, therefore you have very small intervals. There's disadvantage here because of the steps. Again, because computers nowadays are faster, therefore the intervals are small, so the steps are small. But nevertheless, there are limitations for digital systems. There are also, of course, advantages. Digital systems are much more resistant to external noises. Okay? Because the values it deals with is crystal clear, 0 and 1. So it doesn't mix. So if it's 0.5, it doesn't deal with 0.5. So anything sort of below 0.5, that will probably be a 0. Anything above 0.5 will be probably a 1. So it really doesn't. So if you have small noises, half away or less than that, then computer just ignore them. Okay, but of course, when when digital systems go wrong, they go wrong drastically. So if 0 becomes a 1, that's quite a big change. Now, so we have A to D to D to A conversion. Now, what we also need to know, to discuss, is how to represent digital signals mathematically. Okay, so we can actually start analyzing and design controllers. So, for example, the diagram I'll give you here is the process. The example I gave earlier. That's you have a continuous time. The computer needs to take in the values. Taking values every interval. Okay, so 0 time, and next time is t, next time is 2t, next time is 3t. So you take that value, convert into zeros and then ones. Okay, so all the computer cares is about this value, that value, that value, that value. Basically, the values in dots. Okay, it doesn't care about what is happening in between. It can't. It's not capable of worrying about what's happening between. So you will have a series of numbers. That is called sequence. So for that particular ft, I'll have f naught bracket, that's this value. And then next one, if I replace t by kt, that's my interval. When k equals to 0, that's f naught. When k equals to 1, that's time equals to t. When k equals to 2, that's time equals to 2t, that's that value. When time k equals to 3, that's this value there. Okay, so this is really the way to represent sampled signals, and we call it sampled sequences. Now, in the bracket, it's really the time. 0 time, t time, 2 time, tt time, 3t time. That's just represent when we get the data. Now, because when we design computer system, we tend to fix the sampling interval t first. So if we know our t's, we don't really need to write it down all the time. So sometimes we just neglect this t, get rid of t, and say this is f0, f1, f2, f3. It represents the same sequence, just that we choose not to repeatedly write down the t all the time. Okay? And sometimes we can even get lazier. We can just say, right, I'm not going to be bothered about the bracket and zeros. I'm going to put that in the subscript. So f0, f1, f2, f3, and fn. Put all these values together, it will give you the complete sequence. So brackets tend to use to represent sequence, whereas f1, f2, f3, these are the elements in a sequence. But sometimes it gets mixed up. Okay, sometimes people choose to represent the sequence without the bracket. But that's really sort of it's less important. Important thing is that you know when you have a sequence, when you are dealing with an individual component. So the sampling process and the sampling sequences are represented in this way. Now I can give you some examples of sampling from mathematical functions. Now in this case, t is a sampling interval. I'm not even trying to use a number. You can use a number, but it really doesn't matter. Now what you normally do is, because the functions in continuous time tend to be represented as a function of t, unless it's a constant. Okay? If it's a function of t, all you need to do is really replace that small t. Replace, for example, this small t with kt, where t, that capital T, is a constant. It's an interval that you choose beforehand. K is an integer number starting from 0. Okay, so 0, 1, 2, 3, and so on. So it's a sampling process is fairly straightforward, unless you have a constant, for example, a step input. Step signal ft equals to constant 1. Now, if you think about the constant 1, it really doesn't matter what time you take a value in. You get 1. Okay, it really doesn't matter what time you get value in, you get 1 because it's a step, it's a constant value. So the sequence or sample sequence of a step signal would be 1s. You fill up the what's inside bracket with 1s. If the signal, the continuous time signal is a t, then this comes. So you replace that t by k times capital T, and therefore fk, this sequence equals k times t, when k equals to 0, 1, 2, 3. So therefore, if I replace k by 0, I'll get the first element, component, 0. If I replace k by 1, I'll get second component, and then 2, and then 3, and so on. Okay. For exponential function, the process is the same. Because it's a function of time, I replace t, that small t, by capital K, k times capital T. So the sequence, this is signal, so t is signal, small t, in continuous time. This represents sequence in discontinuous or in digital systems. Okay, so now this becomes e to the power minus 5k and t. Now, the only thing that changes here is that k. K is a sequence number or interval number. So you replace the first number, k equal to 0, into here, e to the power 0, that gives you 1. K equal to 1, that's e to the power minus 5t. K to the 2, e to the power minus 10t. K to the 3, k equal to 3, e to the power minus 15t. Now, t is something you predetermine. So if you look at this, inside that bracket, every single component is a number. Okay? We're not really dealing with any variables anymore. Okay? These are the numbers. Okay? Because yeah. Same for the sine wave as well. So if I have ft equals to sine 3t, and I have 3k, so I replace that small t by kt, then you do the same thing. Okay? So this becomes 0, this second one becomes 3t, because small k equals to 1, so k equals to 2, you get sine 60. Now interestingly, with sine waves or cosine waves, the interval can give you some surprises. Okay? And in my practice question, I will give you some examples, and I want you to try to tell me what is happening there. Okay, but I'm going to conceal that for time being, but you will tell me some surprises there. Okay? Now, typical approach for digital design of digital control systems, there are two ways of doing it typically. One is you have a plant, you want to design a digital control for it. And so you convert the plant, the transfer function of the plant, for example, into a discrete time representation. And then use that discrete time transfer function to design the discrete time controller or your digital controller. This is the one I highlight on the right hand side. And that approach tends to work quite well when we had slow computers, large intervals. And this is kind of fairly necessary to do things like that. But nowadays, the computers are fast, and it's a lot easier to take a different approach. Now, this is the one I highlighted on the left-hand side. You have a plant. Plant tend to be in the continuous time. So you design your controller in continuous time as well. Now, because the interval is small, the effect of digitalization or the negative effect of digitalization is minimized. We can actually we can find ways to convert continuous time into digital form and then implement that with the computer. This design, is sometimes preferred, this design approach, is because we have a lot more tools to design continuous time controller, and we understand them better. But also the program itself tends to be continuous. So it's a fairly natural thing to do, to design controllers in continuous time and then convert this into discrete time. And this is really something I would be focused on, but we will before, after we lay some mathematical background for it, and we're going to talk about how to convert continuous time into discrete form. Okay? So I got some practice questions for you. I have 1, 2, 3, 4 different continuous time signals, and I said, well, you choose two different time intervals, sampling intervals. One is 0.1 second, the other is 0.5 seconds. I'd like you to find the sequences of these signals or take a sampling. Then what I really like to do is actually try to see the difference between 0.1 and 0.5, their effect on the sequences you get. Are there any surprises? Okay, give me your thoughts. Okay, thank you.